Hello and welcome to our session for physical sciences. My name is Tem. Today we are focusing our attention on resistance in the context of electric circuits. Right. Now, let's try and understand where we come from in as far as resistance is concerned. By now, we are familiar with some of the concepts that we've looked at in terms of materials in as far as physical properties are concerned. We are able to classify or identify examples of conductors as well as insulators. We also know that a resistor, in essence, is actually an electrical component or a device that we put in an electric circuit for a number of reasons. And these resistors can either be connected, excuse me, in series or in parallel. Right. So in as far as terminology is concerned, what is very important is that defining terms is a very important part of the language that we use in science. And remember, the examination guideline becomes what is acceptable in terms of defining terms, right? And what is also important is that whenever you define a concept or a term, a principle, a law in science, is that you need to capture the key words in that definition. However, it's also very important that you use those key words in the correct scientific context. In other words, it should convey, the keywords should convey the accurate or the correct meaning of that term. Right. So what are some of the terms? We talk of a conductor as a type of material. So these are types of materials. Conductor and an insulator are types of materials, right? And what we know is that in most non-metals are insulators, while most metals are actually electrical conductors, with a few exceptions here and there. And this actually takes us back to our periodic table of elements, okay? And also, the other key term is resistance, as well as resistor. So resistance is actually a physical quantity, right? So resistance is a physical quantity, okay? While a resistor is a device, okay, or a component. So it's very important because the two words are used interchangeably to mean the same thing, which is not actually accurate. So what we're trying to say is that a resistor is a device or a component, while resistance is actually the measure or the quantity that a particular device offers in terms of resistance, as we shall establish through our discussions. So that's as far as the terminology is concerned. Now let's look at the concept of resistance as a quantity, right? So resistance is actually the measure of the opposition to the flow of charges in an electric circuit, right? Now remember, the moment we start to have moving charge through a conductor, okay, then to some extent, in reality, we have got some opposition to that flow or to that movement of charge, or opposition to the current, which is actually what resistance. So an indication or the measure of how much that flow is opposed is what we would refer to as electrical resistance. So the context is electrical resistance, because resistance is a term that can be used loosely in different contexts to mean, you know, a different meaning. But at the end of the day, it has to do with more or less the same thing. But in a conductor, we talk of resistance to the flow of electric charge. Right, so the symbol is capital letter R, okay? And then the component, as we represent it in electrical circuit, will be something with a block and pieces of conductors attached to it. So the SI unit is the ohm. Now in real life, this is a typical example of a resistor that we used in, in electric circuits in our labs at our different schools, right? So that's how it looks like. This is just but one example, right? Okay. Now, let's talk about resistance of a conductor, okay? The battery is the primary source of energy. So the battery provides energy for every coulomb of charge in the conducting material. Remember, the battery is the source of energy, because we know that voltage is equals to work done or energy for every coulomb of charge. So that's why we're saying the battery provides energy for every coulomb of charge. So for this charge to move through a conducting material, there must be some energy, and this energy primarily comes from the battery or the cell, right? Okay. Now, we know also that current is the rate of flow of charge. So mathematically, we've got this equation, I is equals to Q over delta T. So the moment we start have charge passing through a point while moving per unit time, we can talk about current, right? So current is measured in amperes, while voltage is measured in volts, right? So this is what we already know. And now, when it comes to resistance, resistance is actually the measure of the opposition to the moving charge. So if we can conceptualize this, suppose we've got charge within a conducting material. For that charge to move between any 2 points, there must be some source of energy, okay? Now, what the voltage does, the voltage actually provides the energy to move the charge, which we have current. And then the opposition to that moving charge or to that flow of charge is actually our resistance, as that model demonstrates there. So there's a relationship that exists between voltage, current, as well as resistance. So voltage has to do with energy for every coulomb of charge, while current talks to the amount of charge that moves past a point in a given time. So the resistance to that moving charge or the opposition becomes the actual resistance, right? Okay, now we'll go to a simulation to show how exactly charge moves through a circuit in terms of the microscopic view, right? So if we can quickly go to our simulation, right? Okay, so if we close the switch, okay, because before we close the switch, we're saying that the battery provides voltage. Suppose that source has got a voltage of 9 volts, okay? And then we've got a light bulb of a resistance 9 ohms, right? So this light bulb is a resistor, okay? In the sense that it offers electrical resistance to the flow of charge. So if we complete this circuit by closing the switch, we can see that charge moves through the battery, from the battery, through the ammeter, via the light bulbs. So this is how charge actually moves. This is how we model the movement of charge within a circuit, right? Okay. And then we've got what is called the conventional flow of charge. We would have realized that in the circuit, charge was moving from the negative to the positive. But by convention is what, if we talk of convention, we're actually saying this is what is standard, or this is what becomes acceptable as the direction of movement of charge, which we call the conventional current. So if we go back to that simulation, we can show the movement by convention. So what is standard is that charge will move, current flows from the positive to the negative terminal. So this is what is, as the arrows indicate, this is what is acceptable or what is standard. Hence, we refer to it as the conventional flow of current. Right? Okay. Okay. So we have seen conventional current as that flow of charge. So in a nutshell, we want to appreciate at this point in time that electrical resistance is a physical quantity that gives us an indication of the extent at which, there is opposition to the flow of charges within an electric circuit. We'll take a short breather for now, and when we come back, we'll explore more, the microscopic view in terms of, electrical resistance. Let's take a short breather for now. Welcome back to our session. We're still exploring electrical resistance. Now let's look at the micro view of what exactly, this opposition of the flow of charge entails in as far as, conducting materials as well as insulators. Right. Okay. Now we are going to look into some of the properties of insulators, but this takes us back to our understanding of, the physical properties of materials as we have looked at it in the past, right? It says here in solids, remember most of these electrical conductors that we use are actually in solid form. Okay, we know that there are 3 subatomic particles, okay, just to remind us of what is important, what we already know. There are 3 subatomic particles, which is the protons, the neutrons, and the electron. Now again, if we go back to the atomic model, we know that protons and neutrons actually occur or are found in the nucleus of an atom of an element, while electrons occupy what we would refer to as the orbitals or the energy levels, right? So we're saying that these protons are in the nucleus, they remain fixed in fixed position in the nucleus, right? And then electrons are tightly held in bonds. Remember, these electrons are actually negatively charged, okay? So charges are not free to move in solids. Why? Because we know that according to the kinetic molecular theory, that within a solid material, some of the properties is that these particles that make up solids, they actually vibrate within fixed position. So our understanding of that, I think, becomes very important to say that, okay, these charges are actually not free to move. As a result, solids usually have, these insulators usually have high resistance. Now, we get to a point to say that if these solids actually have got high resistance, it means, in other words, they are poor conductors. So a good insulator actually has got those properties of a bad conductor, right? So this is based on the kinetic model, right? Okay. And then let's look at what a conductor, in terms of properties, what are some of these important properties that we need to actually understand. So in this solid, we still have the same structure in terms of the atomic model. Protons and neutrons, they're tightly fixed within fixed position. So these particles tend to vibrate within fixed position. But also in these conductors, which are usually metals, some of the electrons are free to move. Right. Remember, we would refer to these electrons as a sea of delocalized electrons. So within a material that is a metal, we've got this metallic bonding that occurs between adjacent atoms, between adjacent atoms of the same element in a metal. So this sea of delocalized electrons actually makes it easy for these charges to move. As a result, there is low resistance. Then a good conductor will have less resistance compared to an insulator. Right. So once the charges are free to move, there is generally low resistance and high conductivity. That's why we are saying that a good conductor is actually a bad insulator. Right. Okay. Now let's look at the micro view model of a conductor. So we are saying that a metal, which is a good conductor, is actually composed of metallic bonds, right? Where in a metallic bond, there are 2 very important things that we need to remember in as far as a metallic bond, the positive kernels as well as the sea of delocalized electrons, which are negative. Right. So we've got positive kernel and the sea of delocalized electrons. So delocalized simply means that these electrons are actually free to move between atoms of the adjacent particles within the same metal. Right. Okay. Now this is the micro view in terms of a conductor. So take note, this is a metallic structure. Okay. What do we mean when we say metallic structure, right? It means this material, when we look at the periodic table, it should be classified as a metal. And we know, your group 1, your group 2, then you've got your transition metals. And then in between, you've got your semi-metals or metalloids. And then on the furthest end to your right of the periodic table, you have your non-metals. So when we talk about the metals, we're meaning it can be any material that can be classified as a metal in a periodic table, or a combination, because we also have what we call alloys, which are homogeneous mixtures, right? So within a metallic structure, what is important, then this is our positive kernel, okay? This is a positive kernel, right? And then what is moving is the sea of delocalized electrons. As you can see from this demonstration, that these electrons are actually free to move. They are not fixed within, around a single positive nucleus. They are actually free to move between adjacent nuclei. So this is a sea of delocalized electrons. Okay, so these are two very important components within the microview model of a conductor. And this actually must be a metallic material, because most metals are actually good conductors, and if a metal is a good conductor, it's actually a poor insulator, right? Okay, now what are some of the factors that affect the movement of charge in a conductor? Right, remember, different metals have got different electron configurations, okay? Because what sets a particular metal apart from the next is its electron structure, or its electron configuration, or its atomic structure, which is going to be different from one to the next, right? So we want to look at some of the factors that affect, the conductivity or the extent of opposition to the flow of charge within a metallic material. So some of the factors that affect the movement or that contributes to the resistance, number one is the type of material, okay? As we've indicated, different elements have got different electronic properties, okay? While also length is another very important factor that we want to discuss. And then we talk of diameter or area. So if we talk of a diameter, it means we're talking about the cross-sectional area. Because if you pick up a material at random, it can be a piece of wire. In most cases, it is cylindrical in shape. Then when we talk of diameter, we're talking about the cross-sectional area of that particular material. So how does the diameter or the cross-sectional area affect the flow of charge or resistance of that particular material, right? And lastly, we'll look at temperature. But before we talk about temperature, what also is important that we need to remind ourselves of is the kinetic molecular theory, that what exactly is temperature, right? Every form of matter has got some form of kinetic energy as we know it. We have already demonstrated that within any solid, be it a conductor or an insulator, particles that make up that material are vibrating within fixed position. So if we talk of temperature, it's the average kinetic energy of particles that make up that particular solid material, right? Okay. And then now we've got a sample of 1 meter long, same diameter, same temperature. Now the resistance that each one of them offers is quite different if you check. Let's say for argument's sake we compare silver and tin. The resistance of tin is most likely almost 10 times that of silver, okay? So it means silver is actually a better conductor compared to tin, because it actually offers a lesser resistance to the flow of charge. And then we've got everything in between. But this is just a sample within, the different types of material. So it says to us, yes, the flow of charge within a material is also affected by the type of material. So different metals offer different resistance, in terms of the electric charge. Right. So the type of material, we're saying that different materials have different numbers of delocalized electrons. So this is the electron configuration, right, as we know it. Okay. This has to do with electron configuration, right? So if the electron configuration is different, there will also be different freedom of movement. So if there is greater freedom, there is less resistance. If there is lesser freedom, there is greater opposition to the flow. Then, therefore, this accounts for the difference in their resistance as well. Right. Okay. Now, based on this microview of metals, I think we are able to predict the effect, okay, the effect of each of these three factors on resistance. So in other words, we are saying, how does length affect resistance? How does diameter of a conductor affect its resistance, as well as temperature. But immediately when we want to explore those mathematical relationships, we also want to think about the scientific process to say there are some variables involved. And when we talk about variables, what comes to mind, we want to think of your independent variable, your dependent, as well as your control variable. Okay, so, and we need to explore each factor one at a time, right? Okay? And then this is the micro view as we know it, right? So if, say for argument's sake, this is the cross-sectional area, the ease with which these charges move also has an impact on the amount of resistance that a material offers, right? Now, if for argument's sake, we are saying that based on this micro view of metals, we can predict this, how does length affect resistance of that material? Okay, so now we assume that we will keep diameter, temperature, and everything else the same. The only thing that will vary as our independent variable is the length. So we are saying the longer a conductor, the higher or lower the resistance. So we need to decide. So we want to think of this as a guess of some sort, right? So if, for argument's sake, we are saying that this is the resistance that it offers, now the longer this piece of wire, if this is a segment of a conductor, if we extend this this cross-sectional area, what's going to happen is it will offer even a greater opposition to the flow of current. So as a result, we can go back and say that the longer the conductor, actually the higher the resistance, right? So there will be greater opposition that will be experienced, okay? Right. And then when we talk about diameter, remember diameter has to do with the cross-sectional area, okay? So if this is the diameter, okay? Now, if there's a greater diameter, what does it mean? It means that there's gonna be less opposition because there's, there are more alternative ways to pass through. So if I can go to that micro view, right, think of it this way. You can use a practical example of traffic. If there is a single lane, which corresponds to, a smaller cross-sectional area, compared to multiple lanes of traffic, the opposition to the flow is greater when there is smaller diameter compared to, multiple lanes, which is greater diameter. So as a result of that, we can simply say that diameter, yes, does affect the amount of resistance. So the greater the diameter, the lesser the resistance. The smaller the diameter, the greater the opposition to the flow, right? I think we can arrive at that, okay? And then based on temperature, we have said that temperature is actually the average kinetic energy of particles of a substance or a material. So we are saying that at a higher temperature, what is actually happening? There is greater haphazard random movement. So at a higher temperature, there is bound to be greater disruptions or collisions which prevents the ease of flow in terms of those charges. So as a result, at a lower temperature, the opposite is true. So at high temperature, there is greater resistance compared to a lower temperature. So we can make that guess and say that at a higher temperature of a conductor, there is higher resistance, okay, of the flow of charge, right? So if these particles were moving much randomly, in other words, there will be greater opposition that will actually be experienced, right? Welcome back to our session. Now we want to focus our attention on exploring resistance further in as far as the 4 factors that we mentioned that actually affect resistance of a material, right? Okay, so if we can recall, we have listed the 4 factors that affect resistance of a conductor, and we said that these conducting materials in most cases are your metals, right? which is based on the bonding of metals, which is metallic bonding. So the 4 factors that affect resistance, it can be the type of material, the length of material, the diameter, or the cross-sectional area, right? So diameter, we can talk about the cross-sectional area if it's a cylindrical piece of wire or material, as well as temperature in terms of the average kinetic energy of particles of a material. So temperature, think of it in terms of the average kinetic energy, which is in terms of the kinetic molecular theory, right? Okay. Now, terminology. In this segment, we want to look at how we design investigations in as far as, trying to establish or try to find a relationship that exists between quantities. So we want to see how each one of these 4 factors actually affect resistance of a material, right? So the 3 that we want to also pay careful attention to is the dependent variable, the one that we're going to manipulate, all right? Manipulate is what we change so that we see the effect on resistance. So this can be any of the 4 factors, okay? Any of the 4 factors, but one at a time, okay? Any of the 4 factors that affect resistance, okay? Usually, actually, this is the dependent, sorry, just to rectify that, okay? What we manipulate is actually the independent variable. We need to get that right. So this is what we manipulate, the independent variable, okay? Now, we are asking ourselves, for argument's sake, if we change length, how is it going to affect, let's say, resistance? So resistance becomes our response variable, right? We need to get that correct. So any of the 4 factors that we manipulate in a given investigation is our independent variable, okay? And by changing either length, temperature, diameter, how does that affect the resistance of that material, which becomes our dependent variable. And then for this mathematical relationship to be true, we also need to also pay attention to the control variable, that which we shall keep constant, so that we are able to say at the end, yes, indeed, this physical quantity, this is how it exactly affects resistance. So our control variable is what will keep constant, right? It's what will keep constant. Right, so that's very, very important. Right, now the first one has to do with length of a conductor and how it affects a resistance. Right, so what are we saying here? We're going to change the length or vary the length of a conductor, same conductor. Now, if we say same material, and then it means the type of material is the control variable. What we're going to change is how long that same material is, and we want to see how it affects resistance. Right, so here's a piece of apparatus that we want to consider. So if we connect this to a circuit using clips, we put a crocodile clip there and there. Okay, this is the actual length, okay? Let's say this is 1 unit of length, and then if we change the clip and put it there, this is actually double the length. So if we connect it between these 2 points, it becomes 2L, okay? Twice the length, okay? This is the single length, 3 times, and then, if this is 1, and then 2, and then 3, it goes on and on. But in essence, what we are saying, we are just changing the length, which is our independent variable, right? Okay, so this is our independent variable. Now, what's going to happen is that we want to also point it out that that width we changed is our independent variable, which is length in this case. And then we wanted to see how that exactly affects the resistance, which becomes our dependent or our response variable. Now, what is it that we kept constant? If we can go back to the same piece of apparatus, you'd realize that this is the same type of material, okay? Now, depending on where we put the crocodile clips, it will vary the length, okay? Now, if for argument's sake, we are saying that the diameter is the same. We try and keep the temperature constant, and the source in the circuit with which we connect that piece of apparatus, the voltage must also be the same. So you do realize that at one point, or at every point of this investigation, the only thing that changes is only one quantity, which is the length, right? And everything else that might have an impact on, the resistance of that material is kept constant, so that we are able to arrive at a relationship that exists between length as well as resistance of a material, right? Okay, now there are different, the effect of length of conductors on resistance. So you'd realize that if you look at this set of data, from 100 to 20, there is a decrease in length, right? But also, if you look at resistance, right, also from 100 to 20, you see that the magnitude of resistance gets lesser and lesser, right? So can we safely say that even if we increase the length of wire, and then also the resistance will also increase. So this data is also saying the same. Most probably this data was obtained from an actual experiment, okay, using the same type of material. The only thing that was varied or changed was the length of the wire, right? So this is the data, right? So we have got resistance versus length, right? Okay. So R is for resistance, L is for length. Now, for these two to be directly proportional, we are saying that if it's a linear graph that we obtain from that set of data and it passes through the origin, then we can say, yes, indeed, resistance, right, is actually directly proportional to length. Meaning, the greater the length, the greater the resistance. The smaller the length, the lower the resistance. So this graph actually gets to prove that particular point. But when two quantities are directly proportional, it simply means that if we plot that data that we obtained from that experiment, and then it produces a linear graph that actually passes through the origin, then we can say, yes, indeed, these two quantities are directly proportional, like it is in the case of length of conductor of the same type of material, same diameter. It is directly proportional to the resistance, meaning the longer the piece of conducting material, the greater the resistance that it offers in that circuit, right? Okay, and then in conclusion, so these conclusions are actually based on the data that we obtained, okay? It's based on our findings that we obtained. So the findings could be the data, okay? Or the results, as well as it could be the graph that we managed to plot using the data. Okay, so we can conclude that the resistance of a conductor is directly proportional to the length of that conductor. Meaning, in short, mathematically, we are saying R is directly proportional to length. Okay, that's what it simply means. Okay, but for two quantities to be directly proportional, remember, for them to be directly proportional, the linear graph must pass through the origin. Linear means straight line, okay? So if we extrapolate it, it should pass through the origin, right? So the origin whose coordinates are 0, 0, right? So that's what is very important in that case. Okay, we'll take a short break for now, and then when we come back, we'll be able to look at more factors that actually affect resistance. See you after the short break. Welcome back to our session. We're still exploring more of the factors that actually affect resistance of a material in a circuit. So we managed to identify 4 factors that affect resistance. It's the type of material, the length of material, the diameter or cross-section, as well as the temperature, right? And then our focus now is to try and, interpret the data that has been obtained in an investigation of one of the factors that actually affect resistance. But what is also important that we need to remind ourselves of are the 3 components within an investigation. We have got our independent variable. In the previous example that we looked at, how varying or changing the length of a conductor actually affects its resistance. So it's the same type of material, same diameter, same temperature. The only thing that we manipulated was length, right? And then we wanted to see how that affects resistance. So in essence, resistance becomes the response or the dependent variable in that experiment. So now we'll look at the other 3, or a combination of them. But let's keep in mind that the variables must be, you need to focus on them in terms of which one is which in terms of, independent, dependent, as well as controlled. Right. So in this case, we have managed to look at length, and we have arrived at a conclusion that for the same type of material, resistance is actually directly proportional to length of conductor, provided it's the same material, right? And we say that for direct proportionality, if 2 quantities are directly proportional, we must get a linear graph, okay? We must get a linear or a straight line graph, okay, that passes through the origin, okay? Okay, so it should pass through the origin. Okay, so that's what it means, right? So that mathematical relationship can only be true if we have got a linear graph which passes through the origin. So we also know that different types of materials actually affect resistance in different ways. Why? Because when we go back to the periodic table, each element will differ from the next or the other in terms of its electron configuration. So we are saying that most of these conductors are actually metals. And if we go back to the model of metallic bonding within metals, we've got those positive kernels, of the nuclei, and which are adjacent to each other, and then around each one of those there is a sea of delocalized electrons. So actually these electrons are free to move within adjacent nuclei. So that's why we are saying that most metals are good conductors and poor insulators. So they do offer different resistance because of their different electron configuration. That's very, very important for us to also recall. Right now, and we also talk about diameter, which is the cross-sectional area, right? So it's the cross-sectional area, okay? So the greater the diameter, the greater the cross-sectional area. And we also speak about temperature in terms of the average kinetic energy of particles. Okay, but remember, these are actually solid. So the average kinetic energy, which is based on the kinetic molecular theory, right? Okay, now here's a set of results of an investigation of cross-sectional area, okay, of a conductor and its resistance. Already, we are able to point out that indeed there are 2 variables, because in a graph, you know that on the horizontal axis, we've got our independent variable, that which we manipulate, change, or vary. Okay, whichever way you choose to look at it. And then on the vertical axis, we've got the dependent or the response variable. So in this case, we've got diameter versus resistance. So the cross-sectional area is in terms of diameter. You can take note of the units. So this is measured in millimeters squared. So that's the cross-sectional area, okay, which is also based on the diameter. And then the response variable, which is on the vertical axis, is our resistance. But then what do we notice from this set of data? You do realize that when there is a smaller cross-sectional area, there is a comparatively that smaller cross-sectional area, okay, or smaller diameter, there is greater resistance, right? And then again, the greater the cross-sectional area or the diameter, for argument's sake, okay, we can take that and put a dotted line. It takes us to that, okay? So at a greater cross-sectional area, there is very low resistance, right? So is there a relationship that exists between these two? We want to ask ourselves that question, right? So what we pick up, or the trend or the pattern that we get from the data, is that when there is a smaller cross-sectional area of a conductor or diameter, there is very high resistance. But then at a very low, at a greater cross-sectional area, there is lesser resistance. So the opposition to flow is actually affected by the diameter at the end of the day. But what is it that we want to establish at this point in time? We want to see if there is any mathematical relationship between cross-sectional area as well as the diameter. But bear in mind, we are keeping everything else the same or constant. Remember, we would refer to those as our controlled variables. Right, so this is the set of data. So interpreting a graph is very, very important. So our resistance then is in ohms in that case, right? Okay, now the question that we're asking ourselves is, what relationship exists between cross-sectional area and resistance? So this is our independent variable, okay? So that's our independent variable. And then our dependent variable is resistance. Okay, so resistance is a dependent variable. Now, and then if there is such a relationship that exists between these two quantities, how can we be sure that the relationship does exist? So these are the big questions that we want to ask ourselves. Right, now we've plotted the graph of resistance versus the reciprocal of the area, right? So there's, remember, in the previous sketch, we had a graph like this where we've got resistance in ohms, right? And then here we've got cross-sectional area. We've got area in square millimeters, right? Okay, right. So now it's the same piece of information. Now what we've done, we've plotted the reciprocal of the area and the resistance. So there is a linear graph that we get from these results, and then we can safely say that this resistance is directly proportional to the reciprocal of the area. But then what does that tell us about the relationship between resistance and area, right? That's the question, right? Remember, at a smaller cross-sectional area, there is high resistance, while at a greater cross-sectional area, there is equivalently lesser resistance. But then if we plotted the graph of the reciprocal of area, cross-sectional area versus resistance, we get a linear graph. Now, the relationship that we want to establish is between cross-sectional area and resistance. So in this case, we would agree that the resistance is directly proportional to the reciprocal. But then in terms of the area and the resistance, they are inversely proportional to each other, because this straight line graph actually passes through the origin, right? So in conclusion, what are we saying? The resistance of a conductor is inversely proportional to the cross-sectional area of the conductor. Now, mathematically, how do we represent that? We're saying R is inversely proportional to cross-sectional area, because this is a linear graph. So then we are indeed sure that this is an inverse proportional type of a relationship, right? Okay, now we managed to look at length, area, area which is also affected by diameter. Okay, we've also managed to look at type of material. We've said that different material offers a different resistance due to its unique electron configuration based on the metallic bonding of that particular element, right? Or it could be an alloy, right? Now let's look at this one, which says, how does temperature of a conductor, right? Not just temperature of a conductor affect the resistance. Now, temperature of a conductor is what is going to be changed, varied, or manipulated. This becomes our independent variable, okay? So we're still consistent with that. This is our independent variable. We want to establish or want to find out how it affects resistance. So resistance is our response or dependent variable, right? So that's our dependent variable. Now, there are 3 metals that were used in this investigation. So this is a set of data that was obtained from, an experiment of some sort. There are 3 metals. We've got gold, copper, and silver. Right. You do realize that, within the first interval of, let's say 600 kelvins. So the kelvins is the SI unit in which we measure temperature, right? So it's the SI unit, so it means that's what is standard. So we want to establish as we vary the temperature of a conductor, what impact does that or effect does that have on its resistance? We would use different metals to say that we make a generalization to say that this change in the temperature generally affects resistance in this way. That's what we want to establish. So this data that was obtained, we'll use it to try and arrive at that conclusion. Right. You do realize that at a lower temperature, a room temperature is usually between, your 400 and 600 kelvins, for argument's sake. Then within that temperature interval, you realize that there is a more or less linear relationship. But as we increase the temperature, there's that linear relationship kind of does not exist anymore. As you can see with gold, what is happening, it changes from that trend. It's no longer linear. Now, we are saying that the resistance of a conductor increases as the temperature of the metallic conductors increase. So if we go back to the micro view of a metal, remember, at a higher temperature, what does that mean in terms of the kinetic molecular theory? These particles are actually moving haphazard or random with greater energy. So the opposition to the flow of these charges is actually greater at a higher temperature. That's why we realize that as the temperature of that particular conductor increases, what actually happens is there's greater resistance as well. So at a lower temperature, there's lesser resistance, right? Okay, so we can safely say that this is not a direct proportional relationship. We can also conclude that, right? So in a nutshell, we have managed to look at the 4 factors one way or the other in terms of how they affect resistance. But what is it that we take away from this discussion is that resistance, as a physical quantity, remember this is a quantity, okay? It can be measured, right? It's a physical quantity. Okay. Okay, so let's not confuse resistance to resistor. So a resistor offers resistance. So resistance is the measure of the opposition to the movement of charge. So the greater the opposition, the greater the resistance, right? And then also we know that we use the metallic bonding model of metals. So most metals are actually good conductors, right? So good conductors have got resistance, all right, to the flow or the movement of charge, which is electricity, right? Now, we also want to, at the end of the day, recognize that there are these 4 factors, okay? 4 factors that affect resistance. What are these factors? That's your type of material, your diameter, your temperature, as well as this. Also, a number of them, if you can go back, also we spoke about temperature, okay? We also spoke about length. So these are the 4 factors that are important in as far, okay, as the factors that affect resistance of a material. The other one that we forgot is length. So we managed to look at all those 4 now, and we also established the relationship that exists between each one of them. So this is just an example on how we design experiment, and also we managed to look at the different variables that have to be taken into account in any investigation. Well, that's the time we had for today. See you next time, guys.